Hello and welcome back to the lecture on applied econometry. So in this lecture we are going to talk about autocorrelation, and in this lecture we are going to talk about the consequences of autocorrelation. What happens if autocorrelation is present in my regression? So in the previous lecture we spoke about why autocorrelation is present, and we also spoke about the mathematical expression of autocorrelation. So let me again recap. So why autocorrelation is present? One reason we explicitly mentioned is omitted variable, if there is any omitted variable. So what happens is that because of the omitted variable, which is actually influencing my model, what happens in different periods, the omitted variable will show a pattern, and that is something captured in the error term. So we call it omitted variable bias. Going forward, we're going to explain omitted variable bias in details. So that is one reason we have already explained. The other reason could be model specification error. So what do you mean by model specification error? We briefly may say you have a model that x and y are plotted like a straight line, whereas in reality x and y could have a u-shaped what happens is that when you don't plot it, when you don't get the actual shape, so what happens, uh, the, the the U shape or the other kind of shapes which are not captured, they are actually captured by the error term, and then you can see a pattern in the error term, and ut and ut minus 1, you can see there are some correlations. So model specification error could be another reason. The third reason is measurement error. So what is measurement error? So let's say you do not have some data to actually represent the variable, okay? So what happens, you use some proxy or something, and then you basically leave out a part of it. Now, the part which you have left out, that is really, that is really important, and because it is influencing your model, it is being captured in the error term, and then you see this pattern in the error term. So these are essentially the reasons we usually see why autocorrelation is present. Omitted variable bias is often an important cause, but other causes are also they may also cause autocorrelation. What happens if you autocorrelation? So why should we care so much if, let's say, there are some error terms which are correlated, but why do I care so much? And I'll explain that, and I'll show how that actually matters or how actually that does not matter. All right. So one thing we need to remember is autocorrelation and heteroscedasticity. Let me again write it down. Autocorrelation and heteroscedasticity are pretty close. They're pretty close, and like in heteroscedasticity, we have seen that the because of the presence of heteroscedasticity, the estimator is unbiased, which is a good thing. It actually fulfills one criteria of blue estimator, basically linear unbiased. So you get the unbiased part, but it is not the best. It is not the best. It is not the best because the variance is not the minimum variance, because you can always get an estimator which has a lower variance than the estimator you are estimating when your model has heteroscedasticity. The same is true for autocorrelation as well. The same is true for autocorrelation as well. So the estimator is unbiased, but the variance estimator, because the variance is actually high, so you can always find another estimator which you can have a lower variance or the minimum variance, and that is the problem with if you have autocorrelation. So the variance part could be understandable. So whenever you have autocorrelation, the variance is going to be higher, inflated. But how do I actually prove the unbiased part? So that is what is the main topic of this lecture. I'm going to actually explain why, despite having autocorrelation in your model, your estimator could be unbiased. So let me actually show you that. So let's first start with this simple formula. Let's actually use a new page here. So let's actually write down an equation. We have been using this. So yt is equal to beta, or beta 1, let's say beta 1 beta 2 x2, I guess we are writing, and then you write ut. Okay, now My concern is about beta 2. I want to actually, estimate beta 2. So I always get a B2. This is my estimate of beta 2. And I know this mathematical expression I'm familiar with. This is equal to beta 2. I'm not going to explain it again. So this is how it looks like. Is equal to T equal to, let's say, we write it AT, UT, UT. We have used the same, okay. Now, here AT, where let's say where AT is equal to xt minus x bar by, let's say, s equal to 1 to the xs minus x bar whole square. So note that I'm writing here xt and here I'm writing xs, where x is equal to 1 to capital T. So I'm just using different notation t and s, and I think this xt has a specific value, and I'm just using all these different s's here. Okay, so now with this I will get, now let me take expectation on both the sides. So what I'll get, let me actually use this page itself. So if I, let me use a different color. If I take expectation on both the sides, so I'll have expectation of beta 2, b2 is equal to expectation of beta 2 plus t equal to 1 to t expectation of at ut. I can write that, right? Now, simple expectation rule. Now, if I, now this is a constant term, expectation of beta 2, because beta is constant and this is equal to beta 2, so I don't have any problem with this. But with this one, I am going to claim that I am going to write this as, let me further reduce the size. So I'm going to write t equal to 1 to t. Here I'm going to write expectation of a t into expectation of ut, and when I can do that, only when at and ut are independent. Now how I can write that? All right, so I can write that because there is a Gauss-Markov assumption that x's and the error term error terms are independent. Something for my estimated to be blue, my Gauss-Markov assumption states that these two terms are needed to be independent because at is nothing but the x terms and ut is nothing but the error terms. So they need to be independent. And so using that, I actually, wrote this equation in the following manner. Now, till now, I haven't spoken anything about autocorrelation. Now I am actually talking about the UT, the error term. So let us actually talk about the UT now. So what will be the form of UT, and if I have autocorrelation, what is going to happen? So let's see if we have autocorrelation. And let's say this is an AR1 process. So for an AR1 process, we already know it is going to be UT is equal to UT rho UT minus 1 into some innovation or error term, which is IID. Well, let's say I write it ET, right? So this is how we write an AR1 process, okay? It could be AR2 process, AR3 process, whatever it is, but for simplicity's sake, I'm just doing an AR1 process. Now I can write the same UT here in the form of this equation here, all right? Now let us look at UT minus 1. UT minus 1 could be written as rho UT minus 2 plus ut minus 1. What about ut minus 2? ut minus 2 is equal to rho ut minus 3 plus et minus 2. Okay, so with these equations you can clearly see where I'm going. So let's say this is equation 1, this is equation 2, this is equation 3, and if I substitute 1, basically 3 into 2 and 2 into 1, what I'll get is, essentially I will get, let's say I substitute it here, so I'll get ut minus 1 is equal to rho square ut minus 3, and then I will have my et minus 2, so I'll have rho et minus 2 plus et minus 1, right? So if I have substituted this into this 3 into 2. Now what if I substitute 2? So now I got, like, let's say equation 4, and now I substitute 4 into 1. Let's say I substitute 4 into 1. So what I'll get is that I'll get ut is equal to, now I get this row here, so I multiply the whole thing here. So rho cube ut minus 3 rho square, this is going to be et minus 2 rho et minus 1 plus et. Okay, so now I can see, let's say this is equation 5. Now I can see, I can express ut in terms of some remote error term ut, and then I have all the e terms, which is essentially a series. So I have et minus 1, et minus 2, and as I sort of further express ut in terms of et, so I will get more and more et. So what will happen is, essentially I'll get something like a series, something like et plus rho et minus 1 plus rho square et minus 2 plus rho cube et minus 3, and so on. It will continue like this, so on. Okay, now if I have this, let's say this, the u term that I'll have, so ut minus n or something, that is going to be very, very far away from ut, and that let's say that's the first term, and that's 0, let's say. Now if I have this, I have an infinite sort of express ut in terms of all these different et's. Now I actually come back to the expectation part, which I wrote here, expectation of ut. Now if I want to express the whole equation in terms of the expectation, so I'll get expectation of ut is equal to expectation of the whole thing here, et rho et minus 1 rho square et minus 2, and so forth. Now we know this by from very expectation rule that we have learned previously. It is going to be expectation of et plus rho expectation of et minus 1 plus rho square expectation of et minus 2, and so forth. All right, IID. Okay, they're independent and identical distributed with a mean equal to 0. So if mean is equal to 0 and their IID, so what I'll get is essentially all are 0. Okay, all are 0. So essentially that will give me a value, expectation of ut is equal to 0. So that is a very, very important derivation here, and here I can name some these equations, like the number of the equations. So it's equation number 6, equation number 7, let's say. Now if I substitute equation number 7 to this, I didn't really mark it, so let's say this is equation star. So if I put equation 7 in, let me use a different page, putting equation 7 in equation star, putting equation 7 in equation star, let's say, what I get is this term becomes 0, right? So this term becomes 0. So essentially the result I get is expectation of B2 is nothing but beta 2. Okay, so then the B2, I can claim that B2 is an unbiased estimator of beta 2. Okay, so that's the proof I wanted to do here. So essentially, if the autocorrelation is present, what I can claim is that my estimator is unbiased, but it is no longer the minimum variance estimator. There are better estimators available where the variance is lower, and that is the most efficient estimator. Okay, so with this we'll end the lecture here, and in the next lecture we are actually going to see some of the techniques like Darwin-Watson technique to actually detect autocorrelation. Thank you.